What's going on, everybody? Welcome back to High Peak Education. And I'd like for you to take a look at this problem where we look at angular momentum once again. So, a 1.80 meter radius playground merry-go-round has a mass of 120 kilograms and is rotating with an angular velocity of 0.500 revolutions per second. A. What is the angular velocity after a 22.0 kilogram child gets onto it by grabbing the edge? The child is initially at rest. B. Calculate the ratio of the final to the initial kinetic energy of the system. C. Where did this energy go? Alright, so a couple things to do here. First of all, when we think about this problem conceptually, it's actually a essentially rotational collision. How do we know that? Well, when the child jumps on, if we consider the system to be not just the freely spinning merry-go-round, but the child as well, there's no external torques, only internal torques. So the only internal torque is from the child themselves. And with that in mind, we can also say that when the child jumps on, you can imagine it's like a rotational collision, because the rotational inertia will go up, so the angular velocity should go down. So let's write down the various parts of this problem that we should know. We know that the radius of the playground equipment is 1.80 meters, so let's write that down. Capital R, that's typically what we write down for a big radius of a big, solid, rigid spinning object, is 1.80 meters. We also know the mass of the playground equipment is 120 kilograms. Furthermore, it's rotating with an angular velocity of half a revolution per second. So let's write that down. That's omega initial is 0.500 revolutions per second. Now I could multiply by a conversion factor that 2 pi radians is 1 revolution, but that's going to be 2 pi times a half. So that should be exactly pi radians per second, which is approximately 3.14 radians per second for the angular velocity. Okay, so that's rounded to 3 significant digits. What is the angular velocity? So we're looking for an omega final, question mark, that when a 22.0 kilogram child gets onto it, that is on this merry-go-round, by grabbing on the edge. So MC, the mass of the child, is 22.0 kilograms. Well, the question is, how should we model the merry-go-round and how should we model the child? So, ignore friction and air resistance. Okay, we're not told anything about that in this problem, so we will ignore those things. Furthermore, we can say model the merry-go-round as a solid cylinder. Now a solid cylinder would be the same thing we've talked about in previous problems, as a disk. So we know what the rotational inertia of a disk is. We'll get to that in just a moment. And then finally, model the child as a point mass. You could imagine the child is much smaller than the disk. So if you approximate them as a small little sort of point mass, then you can model them with their rotational inertia and see how the rotational inertia of the system changes. So with those in mind, let's start to write down what we know. So if this thing is going to conserve angular momentum, then we can write that the initial angular momentum equals the final angular momentum for part A. So, but remember, this is not some length, it's like an angular momentum, so you could make this L look a little funny if you want. That's going to be the initial rotational inertia times the angular velocity initial equals to the final rotational inertia times the angular velocity final. Now I let the little gap here to kind of give us a sense of what's going on. So this right here, the initial rotational inertia, I think, is just off the merry-go-round. Okay? So just the merry-go-round. And then the final rotational inertia is that of both. Now let's talk about those. The initial rotational inertia, that of the merry-go-round, should be that of a solid cylinder or a disk. And I think that's 1/2 mr squared. So what's the rotational inertia of the child? Well, the child jumps on at a radius of the same as big R. So this is also equal to little r. And the child is a point mass. That's just mr squared. Little m, little r squared. So this rotational inertia of the merry-go-round should be 1/2 big M, big R squared times omega initial equals, let's put this in parentheses since it's both of them, 1/2 big M, big R squared plus little m r squared. Okay? So little m is the mass of the child. So there we have it. Okay, and then times omega final here. Now notice, how can we simplify this problem? Notice that r squared is in each of these terms here. So if we divided the entire equation through by r squared, I think that would cancel each of these terms. Because again, little r and big R are the same in this case. We could also multiply this equation by 2 if we like, because that'll get rid of the 1/2s. So it'll be big M times omega initial is equal to big M plus 2 little m. That all times omega final. And then we just have to divide. So this is big M, omega initial, all over big M plus 2m. By the way, not all problems work out quite that nicely, because not all the radii are necessarily the same. But let's go ahead and put the numbers in to get this omega final. So the mass of the merry-go-round is big M. That's 120 kilograms. The initial angular velocity was about pi, so that's about 3.14, rounded to 3 significant digits, radians per second. And we divide that by, big M is 120 kilograms, and the child's mass is 22 kilograms. We've got to do 2 times that. 2 times 22.0 kilograms. Okay, let's go ahead and get this number with the calculator. So, alpha fraction stack, numerator over denominator. 120 multiplied by 3.14, all divided by 120 plus 2 times 22. All right, let's get this number. It's about 2.30 rounded to 3 significant digits. About 2.30, and that's radians per second. Notice that the angular velocity is indeed less, because since the child jumps on, the rotational inertia increases, so the angular velocity should decrease from this conservation of angular momentum. Okay, looks good for part A. Let's look at part B. What's going to be the ratio of the initial to the final kinetic energy? So we actually went final divided by initial. So K rotational final over K rotational initial should be 1/2, and then it's going to be the final rotational inertia. So that's going to be this 1/2 big M big R squared plus mr squared. So that's the final rotational inertia times omega final squared. And that divided by 1/2 the initial rotational inertia. That's 1/2 big M big R squared times omega initial squared. Notice that this is 1/2 I omega squared, but all the final values and then all the initial values. Okay, so we can make some simplifications here. So if we multiply the top and the bottom by 2, so 2 times the top and 2 times the bottom, that removes these 1/2s. And then if we multiply by 2 again, that removes these 1/2s and makes this a 2 factor. And then again, the radii could divide out. So this is big M plus 2 little m times omega final squared over, let's see, big M times omega initial squared. Okay, so let's put those numbers in. So we're just getting a ratio of these kinetic energies. So we need big M plus 2 little m, so that's 120 kilograms plus 2 times 22 kilograms. And then that times omega final, which was 2.3, that's radians per second squared. A little out of space, I'm just squeezing it in. But then the initial mass was 120 kilograms just of the merry-go-round, multiplied by the initial angular velocity of 3.14 radians per second squared. Okay, so let's put these values in, and then let's get this. This is going to be dimensionless, because it's just going to be joules divided by joules. So let's do alpha and a fraction stack. And this is going to be, let's see, 120 plus 2 times 22. So let's do parentheses. 120 plus 2 times 22, close off that parenthesis, times 2.3, that's radians per second, and then we square it, and we divide by 120 times 3.14 squared. Okay, so we get about 0.733. So this is 0.733. So that's about 73.3%. So notice the kinetic energy at the end is only about 73% or so of that at the beginning. So the question is, where did the kinetic energy go? Well, the kinetic energy went into some other form of energy. Okay, it could have been heat, could have been sound, could have actually been vibration or friction or something like that. Now, let's assume it's not friction, something not conservative per se, but the idea is that basically we could assume that energy had to go into a different form. So this is kind of similar to a rotational inelastic collision. Inelastic meaning the objects stick together, so the kinetic energy is not conserved. So there we go. So thank you very much for watching High Peak Education. Please smash that like button if you enjoyed this content. Please subscribe to the channel to grow the channel. If you would share this on your social networks, I would very much appreciate it. And I look forward to reading your comments. I will look forward to seeing you in the next video.